one together. And then if you're needing help on any others, you can come see me at advisory after school, whenever, and we will grade this assignment tomorrow. I am going to go ahead and teach the next section today, but we'll look at one together. So this one says SAT math scores have a bell-shaped distribution. So if it's bell-shaped, that's the empirical rule, with a mean of 515 and a standard deviation of 114. So what I want you to do, if you are struggling, draw your picture. Your mean is the middle, so that mean was 515. Okay, then these represent your first, second, and third standard deviations. And so to get those, you just add your standard deviation to it. So if I wanted to get these, my standard deviation was, what did I say, 114. So if you add 114, you get 629. You can use your calculator if you're struggling. So you just keep adding it to get every one of them. So you have your 629, 743, 857. How do I get them the other direction? Subtract. Okay, so if I subtract my 114, and you have to do it 3 times to get all of them, your first, second, and third standard deviation. So that would be a 401, a 287, and a 173. Okay, so everybody understand where I got those numbers? So if you set this up, then that should make answering all the questions easier. So the first question, part A, what percentage of scores is between 401 and 629? So 401 and 629, that's right here. That's the first standard deviation. So what did we say? The first standard deviation of the empirical rule, how much of our data should fall there?
68%.
Okay, part B. What percentage is less than 401 or greater than 629? So less than 401 is all of this. Greater than 629 is all of this. How would I go about getting that? Okay. We did that one in our notes where we actually found the percentages of each of those. You could add up all those percentages. You could also use our answer in part A. We know what's the percentage of that middle block.
68.
And what's the percentage of the whole?
100.
So what could you do?
Subtract.
You can subtract. So 2 different ways. 100 minus 68, or add those up, and you should get 32% for that. Part C says what percentage is greater than 743? So that's just this little table. Okay, if you needed to use, we have that one page in our notes where we calculated all those. We also know, let's say you're on a test and you don't have that graph and you can't remember how we got it. Within 2 standard deviations is how much of our data? 2 standard deviations is 95%, and that is just straight off your formula sheet, right? So that means how much is left for the 2 ends? 5% for the 2 total. So then if you divide that by 2, each one is 2.5%. So if you're struggling, draw this picture and label so you can see exactly what part you're talking about, and that should help. Does that make sense to everybody?
How did you get those? I know you already asked me.
That's okay.
How did you get the numbers underneath it?
I added and subtracted our standard deviation. So our mean was 515, and it said your standard deviation was 114. So this is our middle. So you keep adding 114 every time you get those, keep subtracting 114 to get these.
Okay, thank you.
For our mean, those 2 different symbols.
Yes.
A lot of times I just put the edge to the bar over it. Would you count off even though it's like the whole combination?
Typically no. So like on exams like this, when I'm just jotting down notes for myself to think about it, no, I wouldn't care. Other questions? So, yes.
So that was 2.5 because it goes all the way, right? But
Mhm.
if it was just that little chunk, wouldn't it be like 2.35?
Yes. So if you have more questions, come see me in advisory, come in after school, shoot me an email, stop by in between classes whenever you have time. If we've got some time at the end of class, you can ask too. Let's get that assignment done for tomorrow. Our quiz is going to be Friday, and it's going to cover all the sections that we have covered in this chapter. So that's 3.1 through 3.4, which is what I'm starting today. When did I say your quiz was? Did I say tomorrow?
Friday.
Friday, okay. I meant Friday, but
Oh, you said it right there.
okay. So we're going to spend 2 days on this section. We're talking about 2 different things, measures of position and outliers. So we're going to keep using this standard deviation number a lot. And all I've really told you about standard deviation so far is it tells us how spread out our data is. And I've been kind of vague. I just said the bigger the number, the more spread out our data is. We basically are going to use standard deviation to compare completely different sets of data. So the main way we do that is by calculating what is called a z-score. If you look on your formula sheet, we're under chapter 3. We didn't cover all this stuff. We're not doing like grouped data things, but in chapter 3, second column towards the bottom, we have these formulas for population and sample z-scores. And this z-score is very important. We will use this for the rest of the semester. It's a very common calculation. And it's a way of measuring how far your data is from the mean. So the z-score is distance from the mean in terms of standard deviations. It's saying this point is 1 standard deviation away from the mean, or 5 standard deviations away from the mean. And basically, the further it is from the average, the more unusual the point is. Okay, if you think about test scores, if everybody is close to average, that means your z-score is going to be pretty small. You weren't very far away from what everyone else did. But if everybody had an 80% on this test and you got 100%, you did a lot higher than average. So you would have a higher z-score. You are further from the average. And so what this does is it allows us to take completely different sets of data and kind of compare them. You know, let's say you took a test in here, and then you went and you took a test in Mrs. Fuller's class. And you want to know on which one did you do better compared to the rest of your class. So I'm not just looking at your percentage, which one's the higher percent, I'm saying relative to the rest of the class, which one did you do better? And so we need the z-score to help us do that. So it just allows us to essentially, it's kind of like getting a common unit for everything. You know, you can't compare miles and kilometers unless you put them in terms of a common unit. That's what the z-score really does. It takes 2 different sets of data and gets them in a common unit that we could then compare. Okay, so this is on your formula sheet. You don't have to memorize it. Population and sample, the only difference is basically the letters. Mu and sigma are for population mean and standard deviation. X bar and S are for sample mean and standard deviation. So basically you just take your value, subtract your mean, and divide by standard deviation. So let's take a look at this example. The mean height of males 20 years or older is 69.1 inches with a standard deviation of 2.8. The mean height of females 20 years or older is 63.7 inches with a standard deviation of 2.7. Who is relatively taller? So I'm not asking which of these two people is taller, that's obvious. You know, Kevin's got a bigger height. I'm asking who is taller in comparison to the rest of the people in their age group. Okay? So what we will do is find a z-score for each. So your z is your value. So how tall is Kevin? 8 minus the mean. So Kevin is a male. The mean for the males is 69.1. And you divide by the standard deviation. The standard deviation for our males is 2.8. So value minus the mean divided by standard deviation. In general, we will round our z's to 2 decimal places. If you do more, it's not wrong. I typically start using 2 now because later on we're going to be reading values from tables in our book, and all those tables go to 2 decimal places. So it's not a big deal if you keep more. This is just the standard. Okay, so let's look at Candace. We need her z. So her height was 76. What is the mean for her age group?
66.7.
And the standard deviation for her age group?
2.7.
I round to 2 decimals to get 4.56. So first of all, a z can be positive or negative. What do you think the difference is? What would a positive z mean?
They're above the average.
Above average, and a negative z would be below average. Okay, so both of these people are above average. Which one is relatively taller?
Kevin.
Kevin, because he is further away from the average. You know, average is right here at 0. She is 4.5 standard deviations above. He's almost 5 standard deviations above. So he is relatively taller.
So the number we get out of that tells us how many standard deviations.
So just think about, like, on your bell curve, we measured 1, 2, 3 standard deviations. All right. Questions on this? The second thing that we need to talk about today is percentiles. So if I ask you for a kth percentile, you'll see a P for a percentile and a subscript telling you which one. And it's a value so that k% of the observations are less than or equal to it. So if I said the 50th percentile, basically that's a number so that half of your data is below that. What's another word for the 50th percentile?
Median.
Yeah, remember we've done mean, median, and mode. The median was the middle, so that's the number where half the data falls below it. So we've already done a percentile, we just didn't call it that. So like a first percentile means 1% of your values fall below it. Second percentile, 2% fall below it. So we could calculate any percentile we wanted, and it's just like anytime you get a standardized test score back. You know, it might tell you scored in the 86th percentile. And what that means is 86% of the scores were less than or equal to yours. Okay, so basically 14% were above you, 86 were less than or equal to you. so let's look at this one. I just want to interpret a percentile, make sure we know what it means. So the GRE is a test required for admission to grad school. University of Pittsburgh requires a GRE score of no less than 70th percentile to get into the human genetics program. What does this mean? So I want you to write a sentence telling me, what does the 70th percentile mean? What is that? If you have to score up the 70th percentile, what does that mean? Anybody tell me?
Out of all the people you have to place in the top third, out of 70% of the scores, yours will be here and everybody else's will be there below you.
Okay, so it means out of all the scores, 70% have to be less than or equal to your score. So you have to score high enough that only 30% of the people are above you. The other 70% are either less than or equal to you. So you must have a score so that at least 70% of all other scores are less than or equal to yours. In other words, you're in the top 30%. Okay, you're at 70%, 70% are below you, 30% are above you. Okay, the most common use of percentiles for us is to talk about quartiles. You guys done quartiles before, maybe? You've done box and whisker plots, you've done quartiles, and you just maybe didn't use that term. So quartiles, basically think quarter, they're representing every 25%. So the first quartile is the same as what percentile? Second quartile would be the 50th percentile. The third quartile is 75. And then obviously you would have, we really only talk about quartiles 1, 2, and 3 because quartile 4 means 100% are less than or equal to that, so it's just your highest. So we can divide our data into fourths, that's what a quartile is. You don't necessarily have to draw the picture, so basically if you just want to write down quartile 1 is the 25th percentile, quartile 2 is the 50th percentile, which is also called the median. And quartile 3 is the 75th percentile. So that's what we are going to be calculating most, because in the next section we're going to draw a box and whisker plots, so we have to know how to find all of these values. Look at me. Okay, so we have a group of students who collected data on the speed of vehicles traveling through a construction zone on the state highway, where the posted speed limit was 25 miles per hour. So here are the speeds of 14 randomly selected vehicles. I want to find the quartiles for each of these. So one thing, if you're finding quartiles, just like when we found the median, what has to be true about our data? It has to be in increasing order, small to large, which this one is. Okay, I recommend starting with the one we're most familiar with. So let's start with the second quartile. The same as the 50th percentile or the median, because we already know how to find the median. If we have 14 values, what are we going to have to do? So the second quartile is in the middle, which is basically equal numbers above and below it, which in this case would be in between your 7th and 8th values. Alright, so to find it, we add up the 32 plus the 33, divide by 2. So we get 65 over 2, so 32.5. What does that mean? If the second quartile is 32.5?
At that speed, 32% of people are going under the speed limit.
What percent of people? 50. It's the second quartile. So 50% of the people were driving less than 32.5 miles per hour. Okay. The easy way to find quartile 1 and quartile 3, we're good at finding the median, right? Quartile 1 is basically just the middle of the bottom half. So if I wanted the median of the bottom half, we've got 7 values here, so it would just be so that means quartile 1 is 25%. So 25% of the speeds were less than or equal to 28 miles per hour. Quartile 3 would be, so quartile 3, 75% of the speeds were less than or equal to 38 miles per hour. I could ask you if your data is skewed from this. It'll make more sense. We'll look at it when we start drawing our box and whiskers, and it'll be more obvious then. But we could even kind of make a note here. How far is it from quartile 1 to quartile 2? How far apart are those? 4.5. How far apart are 32.5 and 38? So these are further apart, and so what that means is it's going to be skewed to the right. We're going to have more high values because those are more stretched out. That top percentile there. But again, we'll talk more about that when we start drawing our box and whiskers. I just thought I might mention it now. One calculation we will be doing a lot is interquartile range. This is on your formula sheet, and it's just how far apart your first and third quartile are. So we call it IQR, and it's quartile 3 minus quartile 1. It's kind of like a range, but just using quartiles. It's a little bit better than just a regular range because it adjusts for outliers. When you have major outliers, it's not going to make as much of an impact on the interquartile range. So this is really helpful when our data is skewed. If we have bell-shaped data, standard deviation is our go-to, but if it's skewed, the interquartile range is going to be better for us.
Wait, what's this to do? What's this to show?
It's kind of like a range, but it's just looking at your quartiles. So basically it allows, if you had an outlier, let's say this last one was 95 miles per hour, it wouldn't impact my interquartile rate at all. So it's just a safer calculation to throw out any extreme values. Okay, so let's find the interquartile range for this example. What would you do? So what that means is the middle 50%, so between the 25th and 75th percentile, so the middle 50% of the speeds were within 10 miles per hour of each other. And there's a 10-mile-hour per hour difference between the first and third quartiles. So just to kind of illustrate what outliers do to our data, let's say we add another car. So we have our 14 speeds, and I want to add a 15th car that has a speed of 100 miles per hour. And let's look at what that does to everything. Okay. So let's do, okay, since my stuff's on different slides. Our original data, we had what for our, I want to look at mean, median, standard deviation, interquartile range. Let's put our original data in our calculator to get those values. So here was our original. So you go to Stat, Edit, clear out your list and enter these. We have all 14 values. Then if you go over to Stat, Calculate, one variable statistics. If you scroll through the list, it actually gives you everything. The mean, the first thing, our X bar was 32.1429. The median, we calculated it was our second quartile, but if you actually scroll on down, yeah.
Okay, is this the one without the 100?
Yes, I'm just doing the original data first. So all you have to just go to your list, get your cursor on top of the 100, and delete that one value.
Oh.
Okay, if you look, if you scroll through, your calculator does quartiles for you as well. It has Q1 equals 28. Is that what we had for our first quartile? Median, which is the same as quartile 2, is 32.5. Q3, third quartile, is 38, so you can get all of that on your calculator. I asked for the standard deviation, so that's my S. Interquartile range, which we've already found, just quartile 3 minus quartile 1 was 10. So now let's do this with our new data. So go back to your Stat, Edit, and just go to the bottom of your list and add in a 100 for your 15th value. So the mean, the median, standard deviation are all given to you. Interquartile range, you have to calculate. Quartile 3 is what this time? Minus quartile 1. And we get an interquartile range of 11. What do you notice about the means of these two things?
Jump.
Huge jump. What else changed a lot?
Standard deviation.
Yeah. What about the median and the interquartile range? They're very similar. So what this tells me is if we have bell-shaped data, we want to use the mean and the standard deviation. That will be our best information. But if our data is skewed, we see that the mean and standard deviation change a lot, so our safer bets would be to use the median and the interquartile range, which we've already talked about that with the mean and median. Now we're comparing standard deviation and interquartile range. One value makes a huge jump in my standard deviation, but the interquartile range barely changed, so that's a safer bet. I have one last thing to talk about. Do you want me to just finish it and then work day tomorrow?
Yeah.
Okay. So pretty much everything we're doing today is leading us up to box plots, which we will do in our last section in this chapter. So Tuesday, I guess, we'll cover box plots. Do you guys, when you've done box plots in the past, have you had to find outliers? Remember, you would sometimes have, I don't know, did you guys ever just have points where it was so far out, you just put a dot out there because it was really away from all of your other data?
I don't even know what box plot is.
Okay, then I'll quit talking about it. Boxing was good. Well, I'll just wait until next week. So, we have to be able to find outliers. Basically, with a lot of stuff we're going to calculate, an outlier makes a huge difference, and so a lot of times we'll just throw those out. You know, if I give a test, but let's say AJ is absent, and so I put in a 0 in my gradebook for him. Does that 0 have a big impact on like the average of my test?
Yeah.
Yes. So if I really want to know the average of my test, I would take his 0 out and look at the rest of you. So a lot of times that's what we need to do. If we have an outlier, we need to just take that data point out to look at everything else. So we need to know how to find outliers. And that is done by finding what are called the upper and lower fence. So if you look on your formula sheet, that is on there. So to check for outliers, find the upper and lower fence. The lower fence, and this is on there so you don't necessarily have to write it down, it's quartile 1 minus 1.5 times the IQR. Upper fence is quartile 3 plus 1.5 times the IQR. So calculations aren't hard. Basically you find these and those are your boundaries. So anything smaller than the lower fence or anything bigger than the upper fence would be an outlier, and we throw it out. So I would like to do this with our set of data that we were just using, our speed data with that 100 mile per hour in there. So if I want to check it for outliers, we have to find the lower fence and the upper fence. So my lower fence starts at quartile 1, which that's still in our calculator, isn't it? Your one variable statistics. What was our first quartile for this one?
28.
Okay, then we need to subtract 1.5 times, what was the interquartile range for that one?
10.
11. 10 was the original set, but our
Okay.
set with the 100 was 11. Okay. So then if we calculate that, we get a lower fence of 11.5. So that means if you have any data points below 11.5, that's an outlier. Do we have any? No, so we don't have to worry there. Upper fence is quartile 3. So in our speed data that we just did with the 100 miles per hour, what was the third quartile?
30.
Plus 1.5 times the interquartile range for that data was 11. And we get 55.5. So that means any speed above 55.5 is an outlier. Do we have any of those? Yes. So 100 miles per hour is an outlier. I'm going to stop here. So we've pretty much covered everything. Tomorrow, I might do an example or two just to refresh your memory, and then it'll be a work day. So here is the assignment for this section, due on Friday. And there will be a quiz Friday. I'll also talk more about your quiz tomorrow.